Yeah, it's,
Is it clear? The audio?
yeah, yeah, yeah.
Okay. Are you able to see my slide now? Just. Is there an echo or is it fine?
Yeah,
Yes, Fanindra?
it's the fan, sir. I will switch off the fan.
Okay. See if you can tilt the camera or the laptop screen a little upwards so that I can see everybody a little more clearly. Because I see more than 3/4 of it is desk. Yeah, that's good. Well centered now. Okay. So I'm just trying to share my screen from the iPad so that I can do some writing and derivations as well. So I'm glad that you're able to visualize the screen clearly. Just, yeah. Are you able to see my cursor also?
Yeah.
Okay, great. Okay. So this is the last slide we had on Monday afternoon session. And we generally talked about it in terms of the materials that are there. So because we were looking at answering various questions about composites, starting from, just see if the recording is going fine. Yeah. Yeah. So we talked about the lighter colored material over there, which you see in yellow. That is essentially glass fiber, and the darker colored is the carbon fiber. I also mentioned towards the fag end of the afternoon class, hopefully some of you are awake, to why the carbon fibers are outlying. I think one of you also answered that question is essentially because they are stiffer and stronger, and therefore you want the stiffer and stronger ones outwards. Okay, so because that's where the maximum stress occurs. In fact, bending stress is linear along the thickness coordinate, and that's essentially what we would like to leverage or take advantage of. So it's not very different from a sandwich construction, just that instead of a aluminum honeycomb core or a foam core, we have a glass fiber reinforced plastic as the core, which will primarily take the shear stresses. Now, the other important thing to notice is the taper. I talked about it in general, but how exactly it is achieved is something I did not, which is why I'm starting with this slide again. So if you see, actually, you start with a large number of plies at one end. And then as you go, you want to simulate a hinge. So as you move towards the left, you see that it becomes towards the left end, it's much thinner. So in between, we want to gradually decrease the thickness rather than in a discrete fashion, because whenever there's a discrete change in the geometry, it typically results in, can you mute your laptop? Because I hear a little bit of echo. So if you can, yeah, whenever you're asking questions, you can just unmute and ask. Thanks so much. Yeah. So if you see, to move from a very large number of what we call as plies or laminae, we want to get to a smaller number at the left end in order to simulate the flapping hinge, to some extent the bearing as well, so that we have it in a yeah, all okay. Okay, so when you want to do that, as I said, you do not want to suddenly drop a large number of plies, because that creates a discontinuity and therefore stress concentrations, which will become a source of delaminations, which means two plies or two layers of or lamina, which get separated from each other. Right now, so now you see that the way it is done is by gradually dropping off the plies. To start with, you see some of the outboard plies as well as the inboard plies are getting dropped in a sequence. So you see this black thing right at the center. So that's essentially a carbon fiber epoxy, which is getting dropped at this stage. Then a few more are getting dropped at this stage, and therefore there's a slight decrease in thickness here, again a slight decrease in thickness, and so on. It continues that way. So more and more plies get dropped. And where the plies get dropped, you typically will have a matrix-rich region as well. And the reason why you have that matrix-rich region is to ensure that the stress transfer takes place smoothly. If you remember, I showcased a situation where you had an unwanted breakage in a fiber in between, and we saw that when there is no matrix, that fiber becomes useless. But in the presence of the matrix, there's an appropriate stress transfer within just a few microns, which is the order of magnitude of the diameter of the ply in this case, and therefore it becomes quite effective. So here, it is not accidental or something that is not desirous, but actually desirous and designed for that you are dropping off the plies, and therefore you have to ensure that the matrix-rich regions at these locations of ply drops take care of the stress transfer between two adjacent cross sections. Okay, so here's another schematic of the same structure, and essentially a location at which there was a delamination, for example, two layers separating out, and which could be quite disastrous because then it will not be able to take the shear if the separation increases, right? So that's the kind of things that we worked for to create a structural health monitoring system where we put a piezo fiber composite over here, not at 0 degrees, but at 45 degrees, because when you put it at 45 degrees, you get an extension twist coupling that we talked about in the previous class as well. So that is ensure the trapeze effect and some advantageous couplings between the pitch control of the helicopter pilot and the centrifugal forces generated because of the RPM of the rotor itself. Okay, so now this is a schematic again of how we put those extra layers. So you see the dark blue layers on the top and the bottom are essentially your not regular structural composites like E-glass or S-glass or even carbon epoxy, but instead what we call as a lead zirconate titanate, which is an example of a piezo ceramic, and it comes under various classes. So 5H is a certain category of that particular ceramic, but not the entire layer is made out of that. It's a composite, so it's fibers made out of this, either through an extrusion process or through axial dicing. So you have a dicing saw with which you cut, and then you embed that in the epoxy. Okay, so now usually this is most piezo ceramics, including PZT5H, are very heavy. In other words, their density is much larger compared to e-glass or most of the structural composite fibers, and therefore, if you have a very large thickness, you could have an issue. But the fact that we are putting in the outliers means that we take advantage of the largeness of the axial strain generated because of the bending and flap, and which are wherein the top surface is under compression and the bottom surface is under tension. So we tend to extract that information quite accurately. And because this is in turn coupled to the twist of the blade, we can very quickly detect a delamination, and the false alarms are also very less. Because you see, when you're designing a structural health monitoring system, not only do you want to very rapidly detect a damage or initiation or growth, but you also want to ensure that there is no uh, false alarm. In other words, when there is no damage, it should not issue an alarm, and therefore cause delays or inefficient operation of the helicopter fleet as a whole. So that's the reason why we pay so much attention to these kinds of things. So that's just a pure composite in between. Now here you have a composite as well as a foam in between, a sandwich kind of a construction, because if you had seen this, maybe it's not evident over here, but okay, so let me put that. I probably didn't include that picture, which showed the foam a little more explicitly. So let's move forward, right? Are there any questions so far? Okay. Yes, Anay? Okay, you're done. You're good.
Do you have any
Okay, let's.
questions?
Okay, okay, thanks. So next, let's move on to the main core of this course, which is into the how. So we have answered all these questions of what, where, and why. So now we are at a stage where we can actually do the analysis. And in order to do that analysis, we have to have a model, and that's typically a mathematical model. So in terms of certain equations. So if you want to have such a mathematical model, which you can either solve analytically if you have, let's say, a situation where the model is quite simple, or numerically, if it's much more of an involved mathematical model, then you have to do a numerical simulation, which is typically done using a finite element analysis. Now, coming to how you go about modeling the flight vehicle structures, which also includes metallic structures apart from the composite structures. As I've been saying once in a while, the way in which we are dealing with it, only up to the stage where the structure remains healthy. If you have a composite model, just by replacing some of those properties through a much simpler metallic model, you can typically analyze metallic alloys unless they have gone beyond the proportionality limit, in which case the metal becomes more complicated to analyze. So next, we want to see how to model this flight vehicle structures, and in particular, because most aerospace structures these days are made out of composites, how to model a aerospace composite structure. So, in, whatever the model that you might have and how you might want to approach the solution process, either through, let's say, analytics or through numerical solutions, you will have to ensure that there are certain assumptions made, because that's what makes the model distinct from the reality. If you're able to solve the reality as it is, then there's no need for a model. Just because of the complexity of the reality, you want to simplify certain things to make it more tractable to solve, and that's why you have a model in place, right? So if you have to have a model, then automatically there are certain assumptions that are involved. So we will spend quite some time on the assumptions because unless and until you understand these assumptions and the impact of those assumptions on the model and also in its solution process, you will not be able to answer questions regarding the validity of that model when you are applying for a particular situation. So keeping that in mind, let's move forward and understand how the modeling is done in a traditional sense. So remember that we are dealing with a structure which is very, very different from the typical structure that you have with metals, made out of metals. Whereas in a metallic structure, also you will have microstructure based on the crystalline geometry, etc. What happens is you will have the lower length scales like the micro scale, the atomic scale, build up typically handled by material science researchers, not even engineers, right? Or at the most, materials engineers, not typical aerospace engineers, right? On the other hand, when you are going with composites, even this lower length scale is part of our design process. Though of course, we don't go to the atomic level, but we go up to a few microns order of length that we are dealing with a substructure, which is a part of the overall structure. And an analysis of that becomes imperative in understanding the properties and therefore characterizing the material that we are using, not the fiber alone or the matrix alone, but the fiber matrix combination as a whole, because that combo is what we are dealing with as a is that combination that we are dealing with as a composite, right? So now, therefore, the traditional modeling process will involve three different length scales that you see here. One is a very small sized structure, substructure rather, and that is what leads to the so-called micromechanics. And then you have something. So we have a smaller sized microstructure over there. And then we have the actual structure, which could be, let's say, the entire wing or a tail or a helicopter rotor blade, or a part of it, like a spar or a stringer, like the things that we have seen for the reinforcing kind of materials. Or it could even be the skin for that matter, wherein we will go for a 2D model instead of a 1D model. But in all of those situations, jumping from the so-called micro mechanics to the macro mechanics, that is from a very low length scale of the order of a few microns to of the order of a few meters or a little lesser, then it is very difficult to do that as a direct jump, because the way the actual structure is constructed is to get away with some of the disadvantages we talked about fiber composites, that they're very strong and stiff in the 0 degrees, but anything above 45 degrees all the way up to 90 degrees, they are very weak and highly flexible, which could be deleterious for the stability as well as in terms of resonances and things like that, which means that we will have to introduce intermediate geometric scale of analysis, which is not as small as the micromechanics of the order of a few microns, not as large as a few meters, as in the case of the wing or the tail or stringer or a spar, but of the dimension of a particular layer, which could be the generic layer. Just like we say a particular cross section, we do an analysis and call it a generic cross section and apply that with different data for the other cross sections. Similarly, we can do it for a generic layer, and let's say the nth layer, n going on from 0 to very large value, typically about 80 layers or so, whereas here I've just shown 4 layers for simplicity over here. Now, if you take one sample layer like that, let's say the third layer from the bottom or the second layer from the top, which is having an angle plus 45 degrees. In other words, that's the direction in which the fibers are with respect to the x-axis that is shown here, what we have been typically showing in the whiteboard earlier as x1, right? Minus 45 is different from that in the sense that it's in the opposite direction. One is the clockwise, the other is the anti-clockwise. So now if we take a single layer like that, then we can do an analysis at the layer level. And so that becomes the bridge between this micromechanics and the macromechanics. And that's what we call as the mesomechanics. So with the help of micromechanics outputs, we have those as the inputs for the mesomechanics, and the outputs of the mesomechanics becomes the input for the macromechanics, and therefore we have a complete analysis of the structure. Now, this is how it is traditionally done, but the way we approach this at our lab is at a little more advanced level, where we do what is known as a concurrent multi-scale modeling. What we do is not only go from the lower length scale to the larger length scale, but once we identify in the main structure which are the risky areas where stresses are large or deflections are large, for that portion alone, we come in the reverse direction from the large length scale to the medium length scale all the way to the lowest length scale of macromechanics to understand why the stresses are so large in that particular localized region, why the deflections are large. Can we do something about it in order to modify that? So, as I just orally explained, this is in words on the slide. So, mechanics for analysis and design, whether it's analysis or design doesn't matter. It's typically done at 3 sequential levels, a sequential meaning one after the other, and going from the lowest length scale to the largest length scale. Because the ultimate goal is the structural analysis at the large length scale, which is the wing that we are interested in. That's the macromechanics. And irrespective of whether we are dealing with a metallic structure or we are dealing with, let's say, a structure made out of composite, we will have to do that. And the other end of the spectrum, the micromechanics for composites is done more by material science researchers, as I already mentioned, or at the most materials engineers. As aerospace structural engineers, we only do that for composite structures. Now, therefore, the intermediate level, which is only introduced to bridge the gap between the two, is also something that is rarely done with a metallic structure, unless it's like a, let's say, a bimetallic strip or things like that, or a sandwich construction, which is made out of metallic face sheets and a foam core, for example, or even an aluminum honeycomb core, etc. In which case, you will do a layer by layer kind of an analysis, even for a metallic structure. Are these things clear? You can just show a thumbs up and I'll be good to go. Yeah, fine. Okay, now we move on to each one of those individually, and we'll not spend so much time on the micromechanics and mesomechanics, but our goal is more at the macromechanics, which is the structural analysis core of what you're studying in this course 3140. So first, but as I said, without doing these, that makes no sense because you'll not have the data or the input data in order to do the meso and the macromechanics. Therefore, we do have to spend some time on micromechanics. Now, micromechanics by itself is a very large area of research. So we will so we will not venture into all those details of what is the current state of the art in micromechanics, but we will just give a flavor for it with the simplest model and also some kind of an intermediate level model. The simplest model is something that's part of your syllabus, but the intermediate complexity model is just to showcase where it is heading or where you typically can get more accurate results without having to bother about their derivations. So let's start with micromechanics. So micromechanics modeling, if you were supposed to do, as I said, the simplest model that you have is what is known as the rule of mixtures, because just like alloys or any other two or more materials coming together to form a heterogeneous structure, you end up with a mixture. And when you have a mixture, each of those components or constituents of the mixture have distinct properties, usually different from each other, sometimes quite drastically in terms of orders of magnitude. And therefore, you'll have to come up with a solution for how that's going to be done. Okay. So now let's talk about a very simple example. For example, if you're dealing with, let's say, the mass. Okay. Oops. Are you able to see what I write? Yeah. Okay. So now you have, let's say, you want to determine the mass of a particular composite structure, let's say MC. That's obviously going to be the mass of the fiber plus the mass of the matrix, right? Now, mass is a very simple thing. So just to understand the process, I'm taking that example. So mass is nothing but the density of those individual materials times the volume of that. And therefore, if I take this as rho of the composite, which I'm not aware of, because that's a mixture. That's something new that has come out of bringing these two materials together, the fiber and the matrix. So it will just be the mass density of that composite times the uh, volume of that composite, right? So big V subscript C. Okay, C standing for composite. So similarly, for the mass of the fiber, it will be the density of the fiber, which we will know because it might be a carbon fiber or glass fiber. We know its density, right? And then we take its volume, which is the volume of the fiber, and then similarly add the mass of the matrix, which is the density of the matrix, times the volume occupied by the matrix within the mixture. So if this is the case, all of these things are known except rho C, which is what we would like to determine, which is the density of the composite. So if you want to get to the density of the composite as a function of the densities of the constituents, which is the fiber and the matrix, then you see that it's quite simple that all I have to do is to bring VC to the other side. So I will have my rho C, which is the density of the composite, is equal to rho F times VF divided by VC plus rho M into VM divided by VC. Okay. Now these are all uppercase V that I'm using here because my handwriting, from the handwriting, it might not be very clear. So now this fraction that you have here, the volume of the fiber divided by the volume of the composite, is what we call by a small VF, what is known as the volume fraction of the fiber. Similarly, this ratio over here, we call it as Vm to refer to the volume fraction of the matrix. So, see the distinction between the uppercase V and the lowercase v, because I'm not be very clear in my writing, right? So now if this is the case that you have, then in this particular situation, we are taking a very simple mixture where there are no additives. So assume there are no additives. In other words, fiber and matrix are the only two constituents of the composite, right? I'm just taking a few seconds extra to actually write this out explicitly because I want you to understand this process of modeling from a very simple situation, which you can much easily do without even explicitly mentioning these assumptions, because that is what is eventually the danger when you're doing a much more complex model. So when you're doing a much more complex model like that, what you end up with is you don't know the validity because you don't know which assumptions are made. Sometimes assumptions are made, but they're all listed either at the top or at the bottom of the derivation. Then you don't know which assumption is being invoked or utilized where. So it's very important for us to understand not only what all assumptions are involved, but also where they are utilized to make the whole derivation simple. So it's at this stage that we are bringing in this, because then we can say that since there are no other materials, we have the total volume of the composite, that is the uppercase V, subscript C, should be equal to the volume of the fiber plus the volume of the matrix, because the volume of the additives, if they were there, that is zero in this case because there are no additives, right? So that's the reason why if you divide this by VC, the uppercase VC, then you get one on the left-hand side, you get the small vf and the small vm on this side. And so therefore, if we take fiber volume fraction of, let's say, 60%, obviously the matrix volume fraction becomes 40%. Okay, so now I'm beating around the bush for this very, very simple problem, because if you understand this and revisit this obvious thing that you would have probably utilized for various aspects of various courses in the past, not only as undergrads, but even as high school students, then you can very clearly appreciate the micromechanics rule of mixtures as well. So I guess this is more than clear, right? So it's just revisiting something that you already know. Just thumbs up for me to go ahead. Okay. Okay. So now we come to something a little more interesting and directly relevant to what we are doing. This is one of the important equations that we will start with, and this is something which will lead to one of your homeworks. So just pay a little more attention for this. So what we're talking about, E, is a symbol that we have introduced earlier as well, which we know is always the symbol that is used in structural analysis for Young's modulus, right? On the other hand, the E that we have been accustomed to is the Young's modulus for, let's say, metals or metallic alloys, which are typically isotropic materials, and therefore we never cared or needed to use any subscripts. But here you see a subscript L over here, which refers to the fact that it's in the longitudinal direction. Okay. And to be more explicit, I should also say that this is for the composite. It's very similar to the example that we were talking about, the densities, where we had on the left-hand side the density of the composite, which is rho C. Instead, here you have ELC, right, which is the Young's modulus in the longitudinal direction of the overall composite. Therefore, it is ELC. And the structure you see is very, very similar to what we had with the density. Once again, you have a small v that you see over here, which is your volume fraction of the fiber. And this is the volume fraction of the matrix. right? Just that the multiplying factor instead of density is there, because since on the left-hand side we have Young's modulus, we should have the Young's modulus on the right-hand side also. But there you see a slight distinction. So once again, as far as the first term is concerned, instead of ELC, we have ELF, which is the Young's modulus of the fiber. In the longitudinal direction. That's why you have the L over there. So it's, or you can call it the longitudinal Young's modulus. Okay. But on the other hand, for the second term, I'm only writing it as EM. I'm not putting L over there. Can you guess or tell me why that is so? Strictly speaking, I should have written this second term as ELM, right? Why am I just writing it as EM? What does it imply?
Well,
Anybody?
the matrix is three-dimensional, where we didn't restrict any of the dimensions like we did for the fiber or for the longitudinal. So maybe it still
Yeah.
applies.
I think you're heading towards the right direction, but probably not using the appropriate words because you're saying three-dimensional, because everything is three-dimensional here. So what exactly do you mean by matrix is three-dimensional?
Maybe we're talking about like the Young's modulus applies in all directions for the matrix.
Exactly. So what do you call such a material?
Isotropic.
Excellent. Yeah. So the matrix is usually isotropic. In fact, we saw three kinds of composites in the previous classes. Just like the three types of materials we had: polymer matrix composites, very commonly used in aerospace. Then you have the metal matrix composites, and then you have the ceramic matrix composites or carbon-carbon composites. So to some extent, all four of them, but maybe sometimes the fourth one might be an exception. The matrix, whether it's polymer, metal, or ceramic, these are all typically isotropic. So therefore, I don't need to for subscripts to indicate the direction. Okay, so that's essentially an advantage that we have, that the Young's modulus, irrespective of which direction you're taking for the matrix, will be the same. That's why we are just putting it as EM. Now, though this looks exactly identical to the density that we derived, the expression for the density of the composite in terms of the density for the let's say the fiber and the matrix, but the rules of the game or the derivation, the assumptions involved are all slightly different. Okay, the end result is the same or analogous. There's a similarity, but in terms of the derivation, you'll see that there is going to be a difference, and that's once again something that I want you to note. Just like we already talked about an assumption that we already made, this is a second assumption that we are making here, that we are assuming matrix is isotropic. Of course, if it's not isotropic, which is anisotropic, then it's not too much of a difference anyway, because all that we are going to do in that situation is to uh, put a subscript L over there and take the appropriate value of ELM. So it's not going to be a major complication that we are going to introduce, just that since we know a priori that this is isotropic, we're just taking advantage of that, making the equation look a little cleaner by dropping off unwanted subscripts and putting that there. Okay. While we are at wanted and unwanted subscripts, I'd like to point out this innocuous looking E, the Young's modulus, though the way it was introduced to you probably in high school and/or the first year undergrad, is something that really, truly speaking from a mathematically rigorous way cannot be written with just a single subscript because it's not a scalar quantity. When people introduce it through the so-called Hooke's law, as just the stress is proportional to the strain, where I'm using the unusual symbol gamma for the strain instead of epsilon for a particular reason. So uppercase gamma is what I'll use for the 3D strains. So this is a 3D stress, and this is a 3D strain. When I say something is 3D, it means that they depend on all three spatial coordinates, x1, x2, and x3. So if I change any one of these, I'm moving from one point to another in that particular direction, and therefore there could be a change in sigma usually, right? In the most generic case, depending upon, of course, on the structure geometry and the loading and the boundary conditions, etc. Now, if this is the case, then what you just used to write is just sigma equal to a constant of proportionality, E times gamma, and therefore you got that E. Okay. This was well and good for isotropic materials with a uniaxial stress and therefore a strain, the main strain which was resulting out of that. But even in that simple example, there's something called the Poisson's effect. So gamma is not only along the direction in which you're applying the stress. So for example, in this Apple Pencil that I have here, if I pull the ends of this, then not only is it going to extend, but it will also contract in the thickness direction. So it will become thinner because as I extend it. And you can see this more easily in examples like rubber, for example, an eraser, if you're having, and you pull it, eraser made out of rubber, which is an approximately incompressible material. When you're trying to pull it, you can very evidently see the thinning down of the intermediate portion, almost becomes like a dog bone shape, right? So it's very imperative for us, even in that very simple example, to actually take care of the fact that neither your sigma, gamma, or E are scalar quantities. In fact, they are not even vector quantities. You know that vectors are slightly more complicated compared to scalars because scalars only have magnitude, whereas your vectors have both magnitude and direction, right? So now, if you are having both magnitude and direction, you need one subscript. Now, already the way we have discussed stresses, we need two subscripts because one, you have to identify the cross-section on which the stress occurs, and the second, the direction in which the stress occurs. We spent quite some time in, I think last week when we tried to discuss that in the class in person, right? So we are very clear now already that we should have a stress which is indicated with two subscripts, I and J, right? And strain, which is why we call this as a second order tensor or dyadic sometimes, as opposed to a vector, which is a first order tensor, and a scalar, which is a zeroth order tensor. Okay. So now gamma is also a very similar kind of an animal in that you will have gamma. So I'm trying to establish the relationship between sigma and gamma over here. This was for the simple way in which it was introduced in high school physics. Now we are trying to look at it a little more generalized version, understanding that these are 3D quantities, which, as I said, means that these are functions of x1, x2, and x3, the three spatial coordinates. And in fact, in a dynamics problem, you'll have time as well. But nonetheless, you don't call it 4D, but essentially a three-dimensional stress from a spatial perspective. Right. Now coming to the 3D strain, just like the stress needed to have two subscripts because it's a second order tensor, similarly, your gamma is also a second order tensor or a dyadic, and therefore it should also have two subscripts, and we will keep two different subscripts, K and L, because stress in any direction can actually be related to strain in any direction. So it's not that stress in a particular direction should cause strain only in that direction. Yes, that is the major effect. but there is coupling as well, even in as simple a structure as a simple metal bar, which is isotropic, homogeneous, and even at small strains, you know that, as in the example that I just mentioned, where you're trying to pull apart this, you'll have an increase in length, but also a decrease in the diameter, which is the Poisson's effect. So you know that strains in the other directions are also affected. In fact, when you go to composites, this becomes even more complicated because not only are normal strains coupled, that is, if I have a normal strain gamma 1,1 in one direction, I get a gamma 2,2, which is non-zero, a gamma 3,3, which is non-zero. That's fine. It happens even in metals. That's Poisson's effect. But what happens in the case of a composite is, if you have a sigma 1,1, you of course have a gamma 1,1, gamma 2,2, and gamma 3,3. Gamma 1,1, the direct effect, gamma 2,2, and gamma 3,3 are Poisson's effects, but you can also invoke transverse shearing strains. That is, you can have, let's say, gamma 1,3, gamma 2,3, and gamma 3,3, gamma 1,3, and gamma 2,3. So those are the transverse strains, shearing strains that you will have, right? So if that is the case, then when I bring this equal to sign, for an isotropic material, just E might do in terms of a value. But uh, remember that we are not only talking of normal stress and normal strain here, but if I and J are not equal to each other, not having the same value, and if K and L are not having the same value, then it becomes a shearing stress, what we indicated by the Greek letter tau, and it becomes the strain becomes also a shearing strain. So now if you have that kind of a relationship between this, obviously E can't be as it is, because if it becomes shearing strain instead of E, we will replace it with a G, which is the shear modulus instead of E. So to take all of that into account, instead, we can bring in subscripts and superscripts for E as well, which is what we will do over here. And we will put the subscript of the stress, which the E, particular E is relating to, and we will put the superscript of the particular strain that it is related to. Okay, so now this is the actual relationship that you have between any arbitrary stress measure number, sigma ij. Remember, I'm particularly saying it's a measure number rather than a component. We had discussed this distinction between a measure number and a component earlier. A component will continue to be a second order tensor or a dyadic, whereas a measure number like this. So when I once I put the subscripts, I cannot call this second order tensor. What is the second order tensor? Is a sigma double underline. A vector being a first order tensor is single underline, whereas this is double underline. That is your dyadic. Now, a particular measure number in a particular coordinate system is what sigma ij is, given a particular values for I and j or k and l, all of which can take on the values 1, 2, or 3, right? Because it's a 3D model that we are looking at and a 3D space of x1, x2, x3 that we are interested in. So is this clear so far?
Yeah.
So any questions? Yeah. Okay, good.
No question.
Any questions? Okay, good.
No.
Thank you. So now there is an interesting simplification in the way in which this particular equation is written, because as I said, once you have a stress or a strain in a particular direction on a particular cross section, you can have stress or strain in general as a result of that in any direction, in both normal as well as shear. So if that is the case, then we need to see that there's not a particular gamma KL here, but all the gamma KLs on your right-hand side. So if that is the case, then I should actually be writing this particular equation. Let me just erase a few things over here. Okay. Okay. Okay, now, truly speaking, I should have put here, over here, a double summation over K and L, both going from 1 to 3. So in other words, there are 9 strain components, just like there are 9 stress components, because they have 2 subscripts. Each of those subscripts can take 3 values. So you have a combination of 3 into 3, which is equal to 9. Okay, so you have 9 measure numbers, which when put into a matrix form is typically written this way: gamma 1, 1, gamma 2, 2, and gamma 3, 3. Yeah, so gamma 3, 3, which are the normal strains because they have repeated indices. In other words, K and L are equal to each other. And then when they're not equal to each other, which we will write as gamma 1, 2, gamma 1, 3, gamma 2, 3, gamma 2, 1, gamma 3, 1, and gamma 3, 2. Okay. Now, there is something called the engineering strain and the tensorial strain. These gammas that we have introduced over here are what are known as the engineering shear strains, and therefore, and engineering normal strains, and therefore, we need to correlate this with the tensorial strains. So we will come to that a little later, but just out of convention, we take half of that and we put a factor 2 only for the shear strains. Why this is so is because your engineering strain is defined as when you're applying a shear stress, what is the change in the angle, which is the right angle from 90 degrees, increase or decrease, how much does it change by? Whereas for tensorial operations, if it has to be in the form of a dyadic and conform to the usual rules of tensors, you should have half of that factor, which is why we introduce gamma as the tensorial strain. We bring in these factors of 2 in order to account for that. So this is what is your overall gamma. Once again, remember, I'm not putting a double underline under gamma because even though gamma originally is a second order tensor with a double underline because of the order of the tensor, uh, that is something which is generic. Okay, this you will very clearly understand if you look at how vectors are denoted. For example, if you have a, let's say, a vector, let's say V is a vector, then there are many ways to write this, right? So one of the ways in which you would write the vector V is as V1 along the unit vector B1 plus V2 along B2 plus V3 along B3. And in fact, I had written something very similar over here. I think it's better. Okay, so now, as I said, your V1, V2, and V3 are measure numbers. Just jogging the memory, I talked about this earlier. Whereas if you take V1, B1 together, that is what is a component. Okay. So a component remains a vector, whereas the measure numbers are scalar quantities. Okay, because they do not have that B1 multiplying with V1 or a B2 multiplying with V2, etc. Okay. So that being the case here also, when we are writing in the form of a matrix over here, that is not a vector. So that's not a dyadic. Okay. So to take the analogy of the vector in the same direction, let me Okay. Okay, so you would have seen vectors many a times. We write it as a column matrix like V1, V2, V3. Okay, so now I can write this as V, but I cannot write it as vector V. Okay, so that is wrong. Because once I put it in the form of a matrix, that is no longer a vector. It is because you have chosen a particular coordinate system. In this case, you have chosen the unit vectors v1, b2, b3. I could have chosen instead of a particular b1, b2, b3, something which makes an angle with it, a set of angles with it, let's say a1, a2, a3, then the numbers I have for v1, v2, v3 will be different. So therefore, the column matrix that I would have is different, but the vector is the same. It's expressed in two different coordinate systems. So once you put it either as a column matrix like this, oops, or a square matrix like this, it loses the character of being a vector or a dyadic, and it becomes just a set of scalars which are arranged in a particular order within a mathematical form, which is a matrix. Okay. In one case, it's a 3 by 1 matrix that you see over here, a column matrix. Here, it's a 3 by 3 matrix, which is therefore a square matrix because the number of rows and columns are equal to each other. So now this distinction has to be very clear. So here I cannot write this as equal to this. I can call it just a gamma. Okay, it's a matrix. But the gamma, the tensor or dyadic that I started with is different. It is independent of the coordinate system that I choose or the unit vectors that I choose. Whereas this gamma without the underlines becomes dependent on a particular coordinate system we have chosen, like b1, b2, b3. In fact, it needs two sets. Unlike a vector, it needs a b1, b2, b3, and again the same b1, b2, b3, or totally different a1, a2, a3. So two sets of bases are required, but they can be repeated bases as well. Once you have that, then you have a matrix, which is a square matrix that you have here. Whereas this is a dyadic or a tensor. Dyadic is a name given to a second order tensor, just like scalar is a zeroth order tensor and vector is a first order tensor. Now, all of these, are they really required for structural analysis? Absolutely, if you really want to understand it from a fundamental perspective, because understanding from a fundamental perspective is much more imperative today than just an implementation on paper and pencil, because that will only give us an intellectual kick, whereas for us to be relevant, either for the industry as an aerospace engineer or for academia as a researcher, in either case, we need to understand the mathematical rigor of these quantities, because once we understand, most of these are just notations and things that make life simple for us when the overall behavior of the material and or the structure becomes much more complex. Then by utilizing these tools, we can make things much simpler. Okay, because now we are talking about very simple things and introducing these mathematical notations, it might look like, why are we beating around the bush? Why are we introducing all these seemingly complicated or complex concepts? But these are things that will simplify our life when we try to apply it to more real life problems, which is what is the purpose of any course for that matter that we take, especially an engineering related course, because unlike science, which is more an applied kind of a thing, so we have to be applicable to what is currently used and what will be used in the future as well. So I think this is kind of clear, the distinction between V and so here also let me. So whereas here it is right to say V because I'm including B1, B2, and B3. But here I cannot say these. So here you see that these two are not equal to each other, one with the underline, one with the without the underline. Similarly here, one with the double underline and one without any underline at all, a dyadic and matrix, a square matrix that is, and they are not equal to each other. So this I want you to very clearly remember, just like we made the distinction between measure numbers, which are scalars, and components, which are of the same type as whose components they are. If it's a vectors components, the components are also vectors. If it is a components of dyadic, then the components are also dyadics. Okay, so that's something that I want you to keep in mind very, very clearly. Okay, so measure numbers being scalars, no underline is required. For components, you do require underline, either one or two or more, depending upon whether it is a vector or a dyadic. But now we have something which is involving four subscripts that you see over here, I, J, K, and L, right? Now, if you have four subscripts like that, obviously, just like a two subscript thing is a second order tensor, this is a fourth order tensor. So when you want to relate two vectors, for example, both are first order tensors, you need a second order tensor or a dyadic to correlate them. Now you have two dyadics to correlate them because both of each of their orders is 2. 2 plus 2, you have 4 as the order of the measure number that is going to be involved in multiplying that. As I said, there is also a double summation that is there, k equal to 1 to 3 and L equal to 1 to 3. And most of the time it is not written explicitly. So the way we have written the equation already is correct. So I don't need to put this particular thing that you see over here, the double summations of k equal to 1 to 3 and L equal to 1 to 3 explicitly, because it is understood by what is known as Einstein's summation convention, where there is a repeated index, because you see that k and L on the right hand side are repeated. There is one k over here and again another k over here. So whenever there a particular index repeats itself, then there is a summation over its entire range. Because we are dealing with Latin indices, KL, etc. Remember, we talked about all of these indices I, J, K, L that you see over here, varying from 1 to 3, right? So because of that fact, it is the summation range is also from 1 to 3 and over all of the repeated indices. Okay, if it's only one index which is repeated, there's a single summation. If there are n indices which are repeated, there's summation n levels of summation for each one of those repeated indices. But there is no summation over I and j, because on the right hand side, I and j both appear only once each. So both of them are appearing over here as subscripts for E, and therefore it is not repeated. Yes, of course, they are there on the left-hand side, but that doesn't matter. It's only on one side of the equation that we look at in order to employ this so-called Einstein summation convention. Just that we engineers, to just make what is actually much more complicated when written in a rigorous manner, in a simplified manner, we bring in these simplicities in terms of conventions so that things appear innocuously simple on paper or in a book or on a blackboard or whiteboard or a gray board as I have here. Is this clear? Do you have any doubts or questions on scalars, vectors, dyadics, about stress and strain being dyadics, and about E being fourth order tensor? Any questions on this and how the relationship between them?
We're good.
Okay, thanks. Okay, so now if we want to do this derivation of EL, how it is related to EM and EF in the longitudinal direction, then as I said, the overall principle is similar to how we derive the density of the composite as a function of the density of the fiber and the density of the matrix. But the assumptions involved and the actual steps involved and the quantities, the physical meaning of those, they all change. So let me do this simple derivation for you because your homework will be based on a similar derivation for a different quantity. Okay, so now let's take the micromechanic model, which is in a simplest form, where I take cuboid of matrix with a fiber in between. Okay, so you see a circular fiber, and in fact, we discussed at length why you need fibers and how having a smaller diameter fiber actually makes it much, much better, right? So now, for this particular exercise, whether I take it this way or I take it like a bimetallic strip, it doesn't make a difference. Okay. So this can be thought of as two strips with an interface. Okay, so something like this, right? Now we know if the let's say the diameter is d, then we have the area of cross section is pi d squared by 4. Whereas if you have the matrix sleeve of dimension a by a, let's say then that is a squared, right? So this becomes your VF, or the fiber volume fraction that you're talking about, the small VF, right? On the other hand, we can get the volume fraction of the matrix because there are no additives in this case as well. So this is how I would like you to, when you explain your homework also, at each stage, invoke the particular assumption and therefore say, I can make this conclusion from the previous step, right? So because there are no additives, I can just take Vm as 1 minus Vf because I've already calculated Vf as a function of d and a, which I know. So therefore, I know what is the diameter of the fiber, what is the area of what we call as this particular thing as a unit cell. Though in reality, we have to go to a little more complex thing called a representative volume element, RVE, which contains a multiple set of unit cells so that there is a behavior is replicated during a homogenization process. So let's not complicate things too much over here. For us, at this level of the course, unit cell is good enough, right? So for this particular unit cell, if I know the diameter d of the fiber and the area, the size of the unit cell in terms of its breadth and height, which I call as A, therefore I can just calculate VF, and therefore I can calculate VM as well. Okay, so let's just keep this aside. All that I want to say is that now, therefore, I can take this top area, I can change the thickness of this in such a way, and also the thickness of this in such a way that the volume fraction remains the same as what I had in this particular model, right? So the first model is more close to what it is, what it looks in reality. The second one is just for simplifying the whole process of the derivation. It's absolutely not necessary, but it makes things a little easier to kind of visualize, which is what we will continue to take. So in other words, these two thicknesses will be different from each other. One will be the fiber thickness, and that is the matrix thickness. So it's actually not an actual material, but it's more of an imaginative material that we're talking about. Because eventually we would want to go to something which is a homogeneous material, which is again a homogenized material, which is also not real. So it is something that you're imagining, because that will help you simplify the other derivations that come beyond that, okay, or give you properties for the mesomechanics and later for the macromechanics as well. So when you have a situation like that, the overall size remains the same. In other words, you keep the A by A cross section the same. You're just replacing it by different set of material properties. So this is how we would typically approach this whole problem. So is this clear? A thumbs up for me if you're good to go. Yeah, okay. So now that's very clear. So now we will deal with just that intermediate step that we talked about. That is, we have something like this along the length. If we cut at any particular cross section, then this is how it looks. Okay, these are the two materials that we have. One is the fibers properties on the top and the matrix properties at the bottom, right? Now, this is a problem which is relating the longitudinal lengths modulus. And if you want to invoke that, very clearly, we have to deal with longitudinal stresses and longitudinal strains, which means I have to apply a longitudinal force, so which is along the length. Okay. So in this case, I can introduce the coordinate system x1 along the length of this specimen. I can introduce on the cross section the other two spatial coordinates, x2 and x3. Okay. So now that we have our coordinate system fixed, we have a simplified model of the fiber and matrix mixture that we have. We also should be very clear now at this stage to introduce an assumption that this particular bond that you have, which you can see both in the case of the section along x1, x3, because this is x3, remember, or you see over here as well, the x1, x2, x3 picture over there, section over there. So both of these refer to a same surface, which is the interface between the fiber and the matrix. In the real situation, you had that as a circular geometry, a cylindrical geometry, circular cylindrical geometry. But now you're just thinking of it as a flat thing. For this particular process, it will really not matter. I could have as well done with that original itself, but just wanted to explore a different dimension here to bring certain simplicities into the whole derivation. Now, the assumption that we are going to make over here is perfect bonding. So that what that means is that nowhere on that interface is there going to be a gap, or essentially they always remain in contact with each other and they can transfer stresses from one to the other without sliding or without creating a gap between them, right? So sliding, remember, doesn't create a gap, but essentially creates a movement between them. So we are making this contact between these two a little more rigorous by making it a perfect bonding. How does that help? Because now the longitudinal modulus means that I have to apply a force on either side of this, right? So I have to apply an axial force, which I will call as F1 because it's along the x1 direction. So it's like this pencil that I'm trying to pull apart, but it's essentially a rectangular cross section. So something like this maybe, which I'm trying to pull apart, right? So when I'm trying to do that, the fact that we have made this assumption of perfect bonding means that the extension that is there, so because we'll start with, let's say, a length L as always, that is when F1 is not applied, the length is L. And because it's a tension, the L is going to increase by a certain amount, which we will call as, so instead of putting a force here, I can also say it's fixed to make it a little simpler. Otherwise, I'll have to divide the things between the two. Okay, so I can just next time onwards, I'd probably use freeform instead of drawing on the slide. So let's see. Anyway, so what we are going to do is that, let's say we can equivalently fix this, because we are going to fix one of the ends and pull the other end. The support will offer that force F1 in the other direction. We don't need to explicitly show that F1 over there. So when you're doing that, this length will increase, and this will become something like this. Though, of course, Poisson's effect will actually contract. So we are not interested in that right now. So we are only looking at what is happening in the X1 direction. So that increase in length that you see over here, I can call it as delta L, right? So now from your basic deformable bodies course, you will know that this ratio of delta L by L is what you're referring to a particular measure number of the strain, which is gamma 1, because it's on the one phase, remember, which is moving here, because this particular phase that is moving that you see over here. Yeah. So this particular phase that you're having is having a normal, which is along the B1 direction or parallel to the X1 coordinates axis. And therefore it's the first subscript is therefore 1 because of that. And the direction of F is along 1, that is the applied load, and the strain we are interested in is the direct effect, and therefore this is coming out of this fact, and this is coming because of this. So that is the 1 that we are talking about. Okay, so in general, we have total of 9 such measure numbers, gamma ij, I and j taking on the values 3 and 3 each. So it's 3 by 3, which is 9. Okay. So now this delta L by L, because of the assumption that we have made, is the same whether it is in the fiber. So delta L of the fiber is equal to delta L of the matrix is equal to delta L of the composite. Because if they were not perfectly bonded, the fiber being more stiff might not have extended so much. The matrix will extend much more because it has a much lower Young's modulus. And therefore, you would see that the delta L M, the delta L subscript M, will be larger than delta L F if it was not perfectly bonded. So and your delta LC will be somewhere in between these two. Okay. But because we have assumed perfect bonding, therefore, this equality that we are talking about now holds, right? They are all equal to each other. If they are equal to each other, because L is the same, you see in this expression for gamma that we had over here, because of this, you will see that your gamma 1, whether it is in the composite or whether it is in the fiber or in the matrix, is one and the same, because gamma 1 is defined as delta L by L. L is the same for both, all three in fact, and delta L is also the same because of perfect bonding. Therefore, the gamma 1s are equal to each other. Okay. Is this clear that the axial strains are all equal to each other? Whether it's fiber, matrix, which is real, and composite, which is an imaginary material, homogenized material that we're talking about. The actual material is heterogeneous because we have two different distinct materials, fiber and matrix, whereas composite is a equivalent homogenized material. Okay, so this C is a composite. It doesn't exist in reality because it's just an equivalent because it behaves in the same way. The real structure being heterogeneous, but this is an equivalent homogeneous material. Okay, that's why this process is called as homogenization. So instead of having a uh, two levels of strips which are joined to each other, we are now talking of a single strip of the total thickness, the other dimensions also remaining the same, L, B, and H. But what we are having is same properties throughout, not half part of it having a fiber properties, part of it having a matrix properties, but all having the composite properties. Okay. Is this clear that the 3D strains are all equal to each other? Fine. Yeah. So that's the conclusion or takeaway that we have had from there. That gamma, oops. Let me just freeform. Able to see this? Okay. So now we have force which is applied, which can be because of Saint Venant's principle. We can think of this as uniformly distributed. So this is your sigma 1, 1. This is your sigma 1, 1. So that sigma 1, 1 is of course going to be different in the fiber and the matrix. There's no reason why these two should be equal to each other, right? Unlike the strain, which we know is should be equal to each other because you have different things in different places. So here you will have a sigma 1, 1 fiber. You will have a sigma 1, oops. Sigma 1, 1 sigma 1, 1 in the matrix, which will not be equal to each other. And then I go for something which is equivalent of both, which is the composite. So you have sigma 1, 1 in the composite. Now I can relate these because I know the area on which this acts is AF, and the area on which this acts is AM, which is the cross-sectional area of the fiber and the matrix. And this is acting over the total area, which is total area of the cross-section, which is AC, which is the area of the composite, right? Now I know that the total force that is there, which is the force that I'm applying, which I call it as F1. So the F1 in the composite, this is F1 in the matrix, this is F1 in the fiber. Now the total force should be balanced because those are the only two materials taking the load, the fiber and the matrix, and therefore your F1C should be equal to F1M plus F1F. So, which means that I can substitute them for the forces in terms of the stresses, multiplying the areas of cross section of each. So then what does that become? That equation just becomes sigma 11 CAC equal to sigma 11 fiber times the area of cross section of the fiber plus sigma 11 the matrix times the area of cross section of the matrix. Now I can multiply this whole thing by the length L, both sides, the left-hand side and the right-hand side by L. Then we know that the area of cross-section times the length is nothing but the volume. So I can put this as sigma 11 C times the absolute volume of the composite plus equal to sigma 11 in the fiber times the overall volume of the fiber plus sigma 11 in the matrix times the volume of the volume occupied by the matrix. Now, once again, just like we did in the case of the density, we can bring VC to the right-hand side. So it becomes, instead of multiplication, division, and therefore becomes the volume fractions, which are the lowercase v's. So sigma 11C just becomes sigma 11F times small vf plus sigma 11M times small vm, right? Now, going back to our Hooke's law in this simplified form, we have that as just the Young's modulus times the and Young's modulus in this case, because it's a composite or a fiber, we have to say which particular direction, which is the longitudinal direction, whereas for the matrix, we don't need to say that. So next, you have Hooke's law. Which implies that I can replace the stresses with the strains by introducing the Young's modulus. On the left-hand side, it's for the composite. So you have that multiplying gamma 11, which is for the composite. Similarly, your sigma 11F is equal to E longitudinal for the fiber times your strain gamma 11 in the fiber multiplied by the volume fraction Vf. Plus, similarly for the matrix, I don't need to say longitudinal because, as you already correctly pointed out, it is an isotropic material. So I can just write this as Em and multiplied by the gamma 11 in the matrix times the volume fraction of the matrix. Okay. Now, from the previous slide, whatever we saw was that all these gammas are equal to each other because of the perfect bonding. So I can cancel out the gammas. And this is the equation that we started out to prove. Okay. So now you can very clearly see that once you go back to this particular slide, that's exactly the equation that we had. Is this derivation clear? Yeah, thank you. Yeah, Ivan, you had a question?
Yeah, can you go back to the derivation?
Yeah, sure.
So from the second line from the bottom, so where again does the volume go for the composite?
You mean this one?
Yeah.
How this came from this, right? So remember, this is uppercase V's referring to the absolute volume. Whereas these are lowercase v's referring to volume fractions. Okay, so what I did is I took this VC, which is multiplying on the left-hand side, and got it to divide VF and VM. Okay, so big VF by big VC became small VF. Similarly, big VM by big VC became small VM.
Is
that clear?
Small c is just equal to 1.
Yeah. So this is in having the unit of meter cube, whereas volume fractions, it's just a fraction. It's non-dimensional. It's one volume divided by another. So as we said earlier, your small VF plus small Vm, which are the volume fractions, should be equal to 1, whereas your big VF plus big Vm should be equal to, that is the uppercase, should be equal to the volume of the composite. Because this is VF is defined, small VF is defined as big VF by big VC. Okay. Similarly, your small VM is also defined as the big VM by big VC. So it's a volume fraction. Is this clear, Ivan? Yeah. Anybody else? Any other doubts?
Can you
Yes,
explain?
Nafis?
Can you explain how you went from area to absolute volume?
What I mean by absolute volume? I'm just trying to distinguish it from a non-dimensional quantity. It's what you understand by volume. It's just the volume that the fiber occupies and calling it as the volume. Okay, so don't pay so much importance to the adjective there. So essentially what I'm saying is it's the total volume occupied. Okay, so I'm just trying to distinguish it from this non-dimensional quantity, which is a fraction, whereas this is the volume that you usually know. It's the volume occupied by the fiber, the volume occupied by the matrix, and the total volume occupied by fiber plus matrix, which is the volume of the equivalent homogenized material, namely the composite. Is that clear, Nafis?
Yeah, I got it.
Any other questions from you or the others? Matt and I? No? Okay. Yeah, so I think it's quite clear how this derivation happened, right? The final result is that the longitudinal modulus of the composite that you see over here is equal to the longitudinal modulus of the fiber times the volume fraction of the fiber plus the Higgs modulus of the matrix multiplied by the volume fraction of the matrix. Now, I think in the text, it might be a little clearer for you what is the distinction between small v's, lowercase v's, and the uppercase v's, or the big v's. Okay, so now that you have understood this derivation, I just want you to do a very similar derivation of a different material property. Remember, in today's class, we have done two derivations. One is the derivation of the density, the mass density. Then we have done the derivation of the longitudinal modulus of the composite. Okay, so the left-hand side, strictly speaking, I should write it not just as EL, but ELC, because that's for the composite. Okay, so where it is not written, it's understood that it's for the composite. So that's what most textbooks also do. Okay, so now the homework is to derive a different quantity, which is known as the Poisson's ratio. Okay, so Poisson's ratio that you are already aware of, we discussed that briefly in a previous class also as a review of what you have done in deformable bodies. But essentially, it's a ratio of the longitudinal strains in two different directions. Maybe let me go back to this. So, yeah. Suppose you have a Poisson's ratio that's essentially defined as the ratio of the longitudinal strains in two different directions, which are normal strains. But in composites, you need to classify by the subscripts. So for example, if I have mu ij, okay? So remember, again, don't get confused between my big V, small v. This is the volume. This is the volume fraction, whereas this is Poisson's ratio. So these are the Latin letters V, which is also used in English, whereas this is a Greek letter, which you pronounce as nu, right? So now, if you have a metal or any isotropic material for that matter, a polymer, ceramic, doesn't matter. In all these situations, so in all those cases that we have, you would have just nu alone without the need for any subscripts. But in materials like just the fiber or the composite, you will have to give certain subscripts because Poisson's ratio is also different in different directions. So when you have things which are different in different directions, then we take advantage of the fact that we can use directions in the form of subscripts, right? So here, always remember that this in this particular notation for Poisson's ratio that the first subscript will be an input and the second subscript will be an output. And that's quite easy to remember as well because input comes first and output comes as a consequence of that, a result of that, and therefore sequentially it comes later, and which is essentially the output. Okay, so I is the direction of the input, J is the direction of the output. Because Poisson's ratio, remember the Poisson's effect itself is, as we saw the example earlier in today's class itself, I'm just pulling across this Apple Pencil along its length. Of course, it's increasing the length in that direction. That's, of course, dictated by the Young's modulus in the longitudinal direction, which is what we were dealing with in the derivation earlier today. But now we want to get to the changes in dimension in the other directions as well, because not only does it lengthen, but it also reduces in cross-section on the other two directions, typical for most typical materials, though there is a possibility of increase for certain classes of materials. Essentially, there's a change in the cross-sectional dimension, maybe even the shape. Okay, so overall, this is what happens, and this is defined as, and I will use probably this symbol, probably I've used it before as well in our class, where I put a triangle above the equal to sign to say that it is the definition. Whereas when I just talk about the equal to sign, is just assigning something or just saying that two things are numerically equal to each other. But here it's a definition in terms of a new quantity that's being introduced, namely nu, the Poisson's ratio, right? Now this Poisson's ratio for ij direction, that is I as input and j as output, will involve a ratio of normal strains. So that those two normal strains that we are talking about are normal means the index for gamma will be repeated. So this is the output, so which is gamma jj, that is the output, divided by the input, which is gamma ii, with a negative sign. Okay. So what does that mean? I'm essentially applying an input strain gamma ii. In other words, I'm trying to lengthen this by a particular value, and therefore the other things, other direction, there is a change in dimension. So I have to specify this by putting a vertical line over there and saying that my sigma ii is not equal to 0. That's the only strain that I'm stress that I'm applying. So the direct result of that is a gamma ii. All the others go to 0. Sigma ij equal to 0 for all I comma j not equal to, let me just probably take an example so then it will become clearer instead of writing it in a generic sense like this. Okay, so let me just erase that. Okay, all others are 0. So let me take an example of new, let me see what I have given for your homework is new LT, which is longitudinal transverse, so which is 1, 2. Okay. So new LT or new 1, 2. Because this is 1 is the direction of the fiber, therefore it's longitudinal, 2 is any perpendicular direction, therefore that is transverse. Okay. I'll just finish this quickly and we'll break for lunch and meet in person tomorrow. Okay, so if I say new 1, 2, according to that definition, the generic definition that I have, it is the output strain gamma 2, 2 by the input strain gamma 1, 1 with a negative sign, because for most materials, this value will be negative, and therefore by putting a negative sign, we are just dealing with positive quantities. That's all. Okay, but there are materials for which, in spite of putting the negative sign, you will end up with a negative value. We will come to that in the next class tomorrow when we meet in person. So here, what I'm saying is, according to that definition, I'm saying only the input sigma 1, 1 equal to not equal to 0, whereas all other sigma ij are equal to 0 for all I comma j not identically equal to 1 and 1. Okay, so for example, your sigma 1, 2, sigma 2, 2, sigma 3, 3, sigma 1, 3, sigma 2, 3, all those will go to 0, and similarly your sigma 3, 2. So you remember there are 9 measure numbers, of which only one measure number is non-zero. All the other stresses are kept as 0. Then you measure using a strain gauge. So it's a very easy test to do. So all that I do is just like to test the Young's modulus. The same test can be used if I just put one extra strain gauge. What did I do to get my longitudinal modulus? I just put this specimen, which of course should be in a dog bone kind of a shape, into a UTM within the grips. I tried pulling this with a load cell after putting a strain gauge uh, parallel to the structure over here. So when I did that, what happened is this went on increasing, and therefore measuring the strain, I know from the load cell the stress that is applied, and therefore stress strain curve slope up to the proportionality limit became my longitudinal modulus EL, which is what we derived earlier for a composite as a function of the same for the fiber and the matrix. Now we're talking of the Poisson's ratio. All I need to do is to put another strain gauge, which is in this direction, which is a transverse direction, or this direction for that matter. So when I have a strain gauge in that direction, I have already one strain gauge in this direction. Now I have another in this direction. I can measure both gamma 1, 1, that is the increase in length per unit length, and I can also measure the increase or decrease in the width per unit width, earlier, whatever original width was there. So that gives me gamma 1, 1 and gamma 2, 2, right? I just have to take their ratios and then put a negative sign in front of them. I end up with that, because in the UTM, remember, already we are fulfilling this particular condition that we talked about over here, that we have only sigma 1, 1 being applied. All the other stresses are 0. That's the boundary condition in a UTM anyway. And that's essentially what you're defining as nu 1, 2. So if this definition is clear, then the homework should also be quite clear for you. What we're talking about is to prove that nu LT is equal to nu LT for the fiber times the volume fraction of the fiber VF plus the nu, which is the Poisson's ratio for the matrix. Strictly speaking, I should put LT there, but because it's an isotropic material, doesn't matter. It's the same Poisson's ratio in any two perpendicular directions. Therefore, just write it as Vn, right? So that what I'm talking about is here. Right? So I'm talking about this VM over here. So you see, because it's an isotropic material. Whereas these subscripts of LT are explicitly required for anisotropic materials like the fiber or the composite. Whereas the matrix usually is a isotropic material. Okay, doesn't matter even if it's anisotropic, the same equation will hold, just that instead of nu m, I would call it as nu LTM. Okay, so it's exactly similar to what we have done, but remember that the loading condition has changed. The measurements that you have to do is not only gamma 1, but also gamma 2 in order to get to the definition of nu LT. So apart from that change, the derivation is similar. Maybe you might have one or two additional assumptions, or may not need some of the assumptions we made. So just take a note of that. Introduce those assumptions exactly at the places where they are utilized or invoked, rather than just doing it in a blind sense. So I think with this, we will stop. If you have any questions on this homework, I'll get back to. I'm calling it 4.1 because the fourth homework will have a couple of other parts as well, and that I will introduce to you tomorrow. So that will be 4.2 and 4.3. It's very similar to your hare and tortoise story. We had a 1.1, and now we are doing a 1.2. Similarly, for the fourth homework also, there are three parts to it, 4.1 to 4.3. All very similar kind of things, but talking of different quantities. If there are any questions, I'll be happy to answer. Otherwise, we will break. Okay. Okay, great. Thank you.
See you tomorrow.
Enjoy your meal. See you tomorrow. Enjoy your meal. Bye-bye.